You know those absolutely massive AI models? The ones that can reason and code like a pro? How in the world do we get them to run on our own machines, without needing a supercomputer? Well, let's dive into that, because we're going to explore a new technology that might just be the answer we've all been waiting for.
But seriously, just think about it for a second. What if I told you there's a way to take one of those powerful AI models and shrink it down to a quarter of its size, but, and this is the crazy part, with almost no loss in its ability to actually think? It sounds way too good to be true, right? Well, that's exactly the promise we're looking at today.
All right, here's how we're going to break it down. We'll start with what's called the Quantization Dilemma. Then, we'll unpack ParoQuant's incredibly clever solution. After that, we're going to put it to the test with two really tough challenges, one about coding and another about following strict rules, before we really dig into what this 4-bit breakthrough means for you.
So, let's kick things off with the big problem, the fundamental trade-off here, the quantization dilemma. We all want these models to be smaller and faster, right? But that usually comes at a really steep price.
So, what exactly is quantization? Honestly, the easiest way to get it is to think about image compression. Imagine you have this massive, gorgeous, high-resolution photo. That's your full-precision AI model. Quantization is basically the process of turning it into a much smaller JPEG. It's way smaller, it loads faster, but, you lose a little bit of that crisp detail.
And that gets us right to the heart of the trade-off. On one side, you've got your full-precision models. They're the gold standard, incredibly accurate, but they are enormous and painfully slow. On the other side, you've got quantized models, like one that uses 4-bit integers, or INT4. They are 4 times smaller and way faster, but they always suffer some kind of accuracy loss.
Now, why is this such a big deal? Look, for a simple model, a tiny little error doesn't really matter. But for a reasoning model, one that has to think step by step to solve a problem, that tiny error gets bigger and bigger with every single thought. It's a snowball effect. And it can take a perfectly good model and lead it to a completely wrong answer. And this is where our hero ParoQuant comes into the picture. It brings a genuinely smart solution to the table, and it's all based on one really groundbreaking insight. Here it is. This is the big aha moment. Researchers figured out that a staggering 90%, 90, of all the complicated math that's normally used to fix these quantization errors, it's completely redundant. You don't actually have to fix everything. You just have to fix the few things that matter most.
So, how do they do it? It's this really elegant 3-step dance. First, they identify the few troublemaker pairs in the model, the ones with the biggest, most impactful differences. Then, instead of trying to fix everything, they perform this really precise rotation and scaling maneuver only on those high-impact pairs. And finally, they bundle all of this up into a single, super efficient command for the GPU. It's like using a scalpel instead of a sledgehammer.
Okay, the theory sounds amazing, but, talk is cheap. Does it actually work? Let's throw it into the deep end with our first test, a really creative coding challenge that I'm just calling the Spider Aquarium Test.
So the task they gave this newly quantized model was pretty wild. They asked it to create a single self-contained HTML file that would generate a spider aquarium. Yeah, it needed multiple spiders swimming around, animated bubbles floating up, and their little legs needed to move. All of it with this dark underwater vibe and super smooth animations.
Now, why is a task like this so incredibly difficult for an AI, especially a compressed one? This is so much more than just spitting out a few lines of code. Just think about everything that has to happen. The model has to plan this whole complex structure from nothing. It has to think through the actual logic of the animation. It has to handle how the CSS for styling and the JavaScript for movement play together. And this is the real kicker. It has to produce a complete working file in one single shot. That is a massive test of its reasoning power.
And the result? It absolutely nailed it. The model spat out a complete working file. No errors, no bizarre AI hallucinations, which is something you see all the time with other quantized models. It proved that it kept all of its creative and logical firepower. All right, on to our second challenge. This one's a bit more subtle, but honestly, it might be even tougher. Let's call it the happy sentence test. And this is all about following strict, non-negotiable rules. The task sounds almost childishly simple. Generate 10 different sentences that all end with one specific word, happy. This sounds incredibly easy for a person, right?
So why do most of these ultra-powerful AI models, even the full-sized ones, completely fall apart when they try to do this?
Okay, the reason this is so tricky is because of how these models are built. They generate text from left to right, always just predicting the very next word. But this task forces the model to plan its entire sentence backward from a fixed endpoint. It's totally against their nature. Most models just forget the rule halfway through, or they try to cheat by using a word like joyful, or they just produce total gibberish.
But the ParoQuant model, well, as the source material puts it, it has got everything right, which is very impressive. Every single one of the 10 sentences was perfectly coherent and ended exactly as requested with the word happy. A perfect score on a brutal test.
So, let's pull all of this together. What does it all add up to? Let's talk about this 4-bit breakthrough and what it actually means for us in the real world.
I mean, the numbers really do speak for themselves. You're getting near lossless accuracy. We're talking almost 99% of the original model's brain power. The model size gets slashed down to just a quarter of what it was. And the speed cost for all this magic? The overhead is less than 10% compared to other popular methods. You're getting almost all of the gain with practically none of the pain.
And here's the real-world impact. This means you can run these incredibly powerful reasoning models on a regular consumer GPU. For developers, this means inference just got way faster and way cheaper. We're seeing top-tier, state-of-the-art results at 4-bit precision, and it works on both NVIDIA and Apple Silicon. ParoQuant is basically closing that massive gap between the giant, full-precision models and their small, efficient cousins.
This technology is making elite-level AI radically more accessible. It's not locked away in some huge data center anymore. So I guess the real question that this leaves us with is a pretty exciting one. Now that this kind of power can run almost anywhere, what are we going to build next?